Okay, it's 3 p.m. I think it's time to start, but let me wait for like couple of minutes so that if other people are joining in, they can join. Meanwhile, if you have any doubts, you can ask from the previous tutorials or the lectures or any other thing if you want to ask. Okay, I guess then we can start. And if others are joining, then they can join. And you can always watch these videos on YouTube. And I hope that you are getting the link. Okay, so for this week in the lectures, what was discussed was multi electron systems, how you can write the spectroscopic terms of multi electron systems. And the other thing that were covered in the lectures was basic quantum mechanics, right? Very basic introduction to quantum mechanics. So today we will be solving problems mostly related to quantum mechanics, and I will include maybe couple of problems which are related to multi-electron systems and how we can write electroscopic terms or the LS coupling or the total angular momentum J. Okay, so to begin with, let's start with some quantum mechanics. Okay, so I'll write down the first problem. So the first problem is that you have a 1D box. Consider a 1D box. So a one dimensional box, and you're given length A. Okay, so it has length A and it has 3 electrons. So having 3 electrons. The question is, what is the lowest energy of the system? Okay, this is the question. And the options are okay. So this 1D box was discussed in the lectures. Still, if you don't know how to write the energy of electrons or any particle, energy of a particle in a one-dimensional potential box, you can let me know and we can derive the result. But for this problem, if we already know what is the energy and how it varies depending on n, then it becomes a very straightforward problem. In case you don't know, please let me know, or you can go again and watch the lectures and we can derive it. It's a very simple derivation, no problems at all. So assuming that we have watched the lectures and we know how to write the energy levels and the energy of each level, so we can then solve this problem. Okay, so first of all, let me draw one dimensional box. So this is how the potential looks, correct? Yeah. So this goes all the way to infinity. So let's say this is 0 and this is a. Okay, this is our x direction. Okay, this is our x direction and this is our potential v. So our particle is then confined in this region, right? So this is the region in which our particle is confined, correct? Between 0 and a. Okay, now if that is the case, we can write the energy, E to be n squared h squared upon 8m a squared. Okay, now this is for a single particle, for one particle, right? And let me also draw energy levels. So let's say this is n is equals to 1, this is n is equals to 2, n is equals to 3, and so on. Okay, n is equals to 1, 2, 3. So what will be the energy for n is equals to 1? We'll just plug in n is equals to 1 here and we will get h squared over 8m a squared, right? For n is equals to 2, we will get 4 times this value. Okay, and for n is equals to 3, we will get 9 times. Okay, so now what is the particle that we have? We have electrons and we have 3 electrons. This is given to us. So for any energy level at a given time, because electrons are fermions and they have spin plus minus half, so at a given time only 2 electrons can occupy a given energy level. Okay, so if we start filling these levels with electrons, what we will get is we'll get 1 electron here like this, which is up spin, the second electron here like this, which is down spin, and now we cannot fill any more electrons in these levels. Now we have to go to the higher level. So this is how our ground state configuration will look like. So we have 2 electrons in n is equals to 1 state and we have 1 electron in n is equals to 2 state. Okay, I hope this is clear. Then once we have distributed the electrons in the energy levels, we can find the total energy. So total energy will be energy of these 2 electrons plus energy of this electron. Okay, how do we write that? Let's write it. So we know energy of each level. So for the first electron, the energy will be n is 1, so just 1 squared, h squared over 8m a squared. Then again for second electron, n is 1, so again 1. But for the third electron, n is 2, so this will become 2. Okay, Clear? Now we can take h square by 8 ma square as common, and what we will get is 1 plus 1 plus 4, and this is just 6, right? So this becomes 6 by 8, and we can cancel. So this will be 3, and this will be 4. So our final answer will be 3h squared over 4ma squared. This is the total energy of the system, the ground state energy, or the lowest possible energy. Okay. So which option is this? Option B. Okay. Any doubts in this one? No? Okay. So just one thing, I would just like to mention one thing. So when solving such problems, we need to be careful what particle is given to us. So if the particle that was given to us was a boson, then all of them could have occupied the same energy state, right? All of them could have gone to n is equals to 1. But when you have fermions, like electron is a fermion, for fermions things are a little different. Okay, for fermions we have to take care of Pauli's exclusion principle, that no two fermions can have same quantum numbers. So here both of these electrons have n is equals to 1, but their spin is different, right? Their s is plus minus half. So this works fine. Okay, they have different quantum numbers, but then we cannot include a third one here, right? If we include the third one, then it will violate the Pauli's exclusion principle. That's why the third one has to go now to the higher energy level. Okay, so once this is done, we can even do an extension of this problem. Let me write it down. So our next question, this will be, in previous question, if there are 10 electrons, and box length is 1 angstroms, okay, then calculate lowest energy of the system. And the units of energy is given to be joules. The options are okay. Now we have same problem, but instead of 3 electrons, we now have 10 electrons. 10 electrons, and we are given that the length of the box is 1 angstroms. So earlier we took length of the box to be a. So first of all we can write that a is 1 angstroms, or 10 to the power minus 10 meters. So this is a, which is given to us. Again, if we draw the energy levels like this, okay, if we draw the energy levels like this, Okay, let's say this is n is equals to 1, 2, 3, 4, 5. Now we know that again these are electrons. So while filling these levels up, only 2 electrons can go in each level at a time. So this will have 2 electrons up and down, up, down, up, down, up, down, like this. Correct? Right? Okay. Now we have distributed the electrons. We know the formula for E. E is simply n squared h squared upon 2m a squared. Right? Uh, is it 2? Is it 8? Yeah, it is 8. Sorry. So 8m a squared. This is the formula. Okay. So for first level n is 1 and then 2, 3, so on. So the total energy will be, we have, let's take this thing common, and then we'll have 2 electrons in the first level, 2 electrons in the second level, 2 in third, 2 in the fourth level, and 2 in the fifth level. So we can write it like this. Okay, again we can take out this 2 common, we can take the factor of 2 outside, and this will be just 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared. Okay, so this 2, let's cancel this out, and let's write it as h squared over 4m a squared, and if you add these up you will get 1 plus 4 plus 9 plus 16 plus 25, and what will be the total value? Okay, so the total value will be this is 25, then this is also 25, 50, and this is 55. So 55 by 4 h squared over m a squared. Okay, now we know the value of a is 1 angstroms, so we can plug it in. We know h, so h is 6.626 into 10 to the power minus 34, and we also know m, right? We know m is 9.11 into 10 to the power minus 31. Okay, so let's plug in all the values, and we can write E to be 55 over 4 into 6.626 into 6.626 divided by 9.1 into 10 to the power minus 31, and this is just 10 to the power minus 20, and here you have 10 to the power minus 68. Okay, so this becomes minus 51. If you take it up, this just becomes 10 to the power minus 17. Okay, great. Now if we multiply these terms, upon multiplying, what we will get is, we will get 67.0 into 10 to the power minus 17, or 6.7 into 10 to the power minus 16 joules. So this is our final answer, which is option B. Okay, any doubts in this one? Anyone? Okay, so this was just extension of the last problem. This was very similar. Instead of 3 electrons, now we had 10 electrons, and just how we fill these electrons. Okay, so we just make sure that each energy level they have 2 electrons, not more than 2 electrons, because electron has spin half. Okay, good. So let's move on to the next one. Which will be question number 3. So what is question 3? So we are given a particle, its mass is m, and its potential energy is u, and total energy is E. Okay, so if the de Broglie wavelength holds good for this particle, then its wavelength in terms of E, U, and M will be. And here are our options. So first is h upon E minus U times M. Then we have h over m under root E squared plus U squared. Then option C is mh times under root E minus U, and option D is h over under root 2m E minus U. Okay, now we are given mass m, we are given potential energy U, potential energy is U, and we are given total energy is E. And what we are asked is, we are asked about wavelength, okay, de Broglie wavelength. Now what is this, what is the magnitude of de Broglie wavelength? So we write, let it be lambda, okay, let it be lambda. So we know that lambda is h over p, correct? Lambda is h over p. So this is de Broglie wavelength. Okay, this is de Broglie wavelength. Now we know h. What we need to find is the momentum. We are given total energy E. We are given the potential energy U. What we need to find is the momentum. Okay. Now we know that kinetic energy, let's say K, this is half mv squared. Half mv squared. Let's multiply by m in denominator and numerator. So then this becomes half m squared v squared over m. Okay. Or we can write mv as p. This is the momentum. So then we can write our kinetic energy as p squared over 2m. Right? And now we just need to find out our kinetic energy. Once we get the kinetic energy, we will get our momentum. Okay, we will get our momentum. So total energy is given to be E. and potential energy is given to be U. Okay, and we know that this total energy is sum of kinetic plus potential. So therefore kinetic energy will be E minus U. This is our kinetic energy. So from equation 1 and 2 we can write P squared over 2m, this is equals to E minus U, or we can write P squared is 2m E minus U, and taking square roots on both sides, so P will be under root 2m E minus U. So let's say this is equation 3, and let's say this is the definition. Okay, so plugging equation 3 in the definition, that is lambda is h over p, so we can finally write lambda is h over under root 2m E minus U. Okay, so this is the de Broglie wavelength, which means option D. Okay, so if we are given the total energy and the potential energy of any mass m, then we can write its de Broglie wavelength in this form. Okay, any doubts in this one? No? So let's solve the next one. So let's go back to our Ellis coupling. Okay, let's solve one problem related to that, and the problem is find the angle between angular momentum vector L and spin vector S. Okay, for the 2d 5/2 term in one electron atom. And our options are okay, these are our options. So first of all, let us look at the spectroscopic term. So generally we write it as 2s plus 1 L and J. And what is given to us? So if we compare these two, the thing given to us is 2d 5/2. So upon comparison, okay, upon comparing, what we get, that 2s plus 1 is 2, which implies s is half. Also what we get is, because we have d, so s means 0, p means 1, and d means 2. So this implies our L is 2, because we have d here, right? And d means L is 2. Finally, our J is 5 by 2. Okay, so we have these three. We have extracted the value of S, L, and J. We now have the three quantum numbers, which we will be using later. Now what does the question ask? Question asks us about the angle. So we have to find the angle between L and S. Okay, so if this is, okay, let's draw a rough schematic. If this is your L, okay, and this is your S, okay, this is L, this is S, and this angle is theta. So we want to find out the value of theta. The question asks to find us the value of theta. Okay, now how do you solve this problem? Okay. To solve this, first we note that we can write J as L plus S. Okay, and now if we square both sides, so we can write J dot J, we can write this as L plus S dot L plus S. Okay, and this just gives us J squared, and this gives us L squared plus S squared plus 2 L dot S. Okay, and now from this diagram, it should be clear that our L dot S will be nothing but magnitude of L times magnitude of S times cos theta, right? If theta is the angle between them. So if theta is the angle and this is L dot S, so what we can do is we can write J squared as L squared plus S squared plus 2 LS cos theta. Okay, or we can rearrange this thing. We can write 2ls cos theta to be J squared minus L squared minus S squared. Therefore our cos theta will be J squared minus L squared minus S squared over 2ls. This will be our cos theta. Now how do you find the magnitudes? So we'll use the value of S, L and J, which we have computed earlier right here. Okay, so we'll use these values. So for example, if you want to calculate the magnitude of J, that will be under root J plus 1 times h cut. Similarly for L, so L will be under root L plus 1 h cut, and S will be under root S plus 1 h cut, right? And we already have the value of S, L and J from our spectroscopic term, so we just need to plug in the values. So if we plug in the values, what we will get? So our J was 5 by 2. Okay, so it will be 5 times 6 square root over 2, and here you have h cut. L is 2, so this will be under root 6 h cut, and s is half, so 1 by 2, 3 by 2, so this will be under root 3 by 2 h cut. Okay, so we have this. And now let's find out cos theta. So we can write cos theta as j squared, which means 30 over 4 h cut squared minus 6 h cut squared and minus 3 over 4 h cut squared. Divide the entire thing by 2 times ls. So L is root 6 into root 3 by 2 h cut. Okay, so this is what we have. This is what we have. Okay, so these twos will cancel out. These twos will cancel out, and let's say we write this as 24 over 4. So this will be 30 minus 24 is 6 minus 3 is 3. So then this will be, and h cut square will also cancel out. So this will be just 3 by 4 over, so this is root 3 and root 2 into root 3. So yeah, so then ultimately what we will get is, we will get theta as cos inverse under root 2 by 3. Okay, and if we put the value in this in the calculator, so we will get 61.9 degrees. Right, this will be 7, so this will be 35. So this will be, okay. Yeah. So correct answer will be option C. Okay, we are done with 4. Let us solve 5th one. Now this time we have a 2 electron system. So for a 2 electron system, we have orbital quantum numbers. orbital quantum numbers are L1 is 1 and L2 is 2. Now the question is that we have to write all the possible values, write all the possible values of total angular momentum quantum number, total angular momentum quantum number J. Under LS coupling scheme. So this is the question, and our options are 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4, 1, 2, 3, 4. So these are the options. Okay. So as we know that there are two coupling schemes. There are two coupling schemes. So one is LS coupling. Okay. Another is JJ coupling. Okay. So one is LS coupling and other is JJ coupling. Now what is the difference between the two? So the difference is here we calculate total L first and then total S first and then we couple them. So if we have, like here we have a 2 electron system. So here step 1 is compute total L as L1 plus L2 and then compute total S, compute total S as S1 plus S2, and then we get J as L plus S. So this is LS coupling. Another thing which is known as JJ coupling. So here we first compare individual J's. So for example, we'll first compute J1 as L1 plus S1. Then we'll compute the individual J2 as L2 plus S2. And finally our total J, that will be J1 plus J2. So this is the difference between LS coupling and JJ coupling. In this problem, we will be using LS coupling scheme. So for that, first we have to compute the total angular momentum, L. So we are given L1 is 2 and we are given L2 is 2. Okay. So the total L, this can have all the possible values from L1 minus L2 from L1 minus L2 all the way up to L1 plus L2, like this. So if you take the difference, 2 minus 1 is 1, so it can go from all the way from 1, and L1 plus L2 is 3. So L can have all the values 1, 2 and 3. Now here S1 is half and S2 is also half. So total S, again it can have all the values from S1 minus S2 to S1 plus S2. So here if you subtract you will get 0 and if you add you will get 1. So these are the total values. So possible values of L are these. Okay, possible L values. And these are the possible S values. So we have completed step 1 and step 2. So we have computed the total L and we have computed the total S. Now to compute J, we just need to add L and S. Okay, we just need to add L and S. So when L is 1 and S is 0, this will give J as okay, again J can have all the possible values from L minus S all the way up to L plus S. Okay, so here 1 minus 0 is 0 and 1 plus 0 is 1 minus 0 is 1 and 1 plus 0 is also 1. So J can have only one value, which is J is equals to 1. And when L is 1 and S is also 1, then J can have three values, 0, 1, 2. Now when L is 2, S is 0, S is 1. So again, L minus S is 2 and L plus S is also 2. So it will have only one value. But here L minus S is 1. So J will have 1, 2, 3. Okay. When L is 3 and S is 0, so J will have only one value, 3. But when S is 1, then J can have 2, 3, 4. Because 3 minus 1 is 2 and 3 plus 1 is 4. So all three values. So from this thing, possible J values will be 0, 1, 2, 3, 4. These are the possible J values, which matches with option C. Okay. Any doubts in this one? Okay. Let's solve one hydrogen atom problem. Okay. So we have an electron for free hydrogen atom which is initially at the state with quantum numbers so N is 3 and L is 2. Okay, so these are the initial quantum numbers of an electron of a free hydrogen atom. Okay, so the electron then makes a transition to a lower energy state. Right? It makes a transition to a low energy state. Now, which of the following states may be possible after this transition. So this is the problem, and let's look at our options. So n is equals to 2 and L is equals to 0, n is equals to 3 and L is equals to 1, n is 2 and L is 2, and finally n is 2 and L is 1. Okay, so what does the question ask us? So we have an electron of a free hydrogen atom. We have an electron in a hydrogen atom. If we try to draw the energy levels, okay, let's at least draw that. This is the nucleus. Let's say this is n is equals to 1, this is n is equals to 2, and then this is n is equals to 3. Okay, let's say this is how our hydrogen atom looks like. So n is 1 here, 2 here, 3 here. So initially our electron is somewhere in n is equals to 3 here. So this is our electron, n is equals to 3 and L is equals to 2. Now the question says that it makes a transition to a lower energy state. It makes a transition to a lower energy state. Now if we look at our options and look at the n values, so we can clearly cancel out option B. Okay, so we can cancel out option B. So option B is incorrect. Why? Because n is equals to 3 is not a lower energy state. That is not a lower energy state. Okay. And the question says that there is a transition to a lower energy state. So now we are left with option A, C and D. So note that we have already used up the information for N, but what we haven't used is the information for L. Now what is the information for L? That L is given to be 2 and there is a selection rule. Okay, we will make use of selection rule. So selection rule tells us that there is a selection rule for a electric dipole transition. Electric dipole transition. The rule says that delta L, this has to be equals to plus minus 1. Okay, plus minus 1. So initially if L is 2, which is in this case, then delta L is equals to plus minus 1 would imply, this would imply that final L can be L final. So if we add 1, we get 3. If we subtract 1, we get 1. So L final can have only these two values, 3 or 1. Okay, but because it is going to n is equals to 2 level, so we can eliminate 3. Okay, we can eliminate 3 because n is less than or equal to 2. So L is equals to 3 is then not possible. Therefore, final L will be 1. Okay, it cannot be 0, it cannot be 2, it can only be 1. So this is correct. Therefore, option D is the correct answer. Any doubts in this one before we move on? And do you want to ask anything?
No, sir, no doubt.
Okay, thank you. Okay, then let's solve a next one. Okay, so next one is related to a polar coordinate system. This was also discussed in the class. So I thought maybe some people would not know much about three-dimensional polar coordinate system. So let me just put in a very simple question for the people who don't know about polar coordinate system. Okay, so we are given a 3D polar coordinate system is shown below. Okay, let's draw one polar coordinate system. Okay, let's say this is our z-axis. Looks a little tilted. Okay, let's say this is our z-axis. This is maybe y-axis, and finally we can have x-axis here. Okay, and then we can take a general point. Let's say this is some general point P. This is point P. Okay, in the Cartesian coordinates we can write its coordinates as x, y, and z, right? So you move, sorry, I forgot to mention x. So you can move certain distance in x direction, and then certain distance in y direction, and certain distance in z direction, and you will get to this point. But another way to get to this point is using the polar coordinates. And how does that work? So let me first draw a vector here. Okay, let us draw this thing. So this is r, the position vector, right? So this is r, which just joins the origin to the point P. Okay, so this is r. Now this r will make some angle with the z axis. Okay, this r will make some angle with the z axis, and that angle, that is known as theta. This angle, this is known as theta. Finally, the if we take the projection of this point P on the xy plane, okay, if this is our xy plane, and we take a projection like this, okay, we can take this projection. Let's say this point is P prime. Okay, this is P prime. So then our final coordinate in the polar system, this angle, which this P prime, the projection of point P makes with x axis, this angle is phi. Okay, so this is how we define a polar coordinate system. So just like in the Cartesian coordinates, you can move x, y, and z, right? And you will get to point P. In the polar coordinates, we have r, theta, and phi. So we have these three quantities. So you tell me the distance r, the distance of the point from the origin, that is r. Then you tell me the angle theta which it makes with the z-axis. I'll turn the angle theta. And then you tell me the phi which its projection makes with the x-axis. And I can uniquely define any point in the space. That is the idea. Okay. Now what is the question? The question is, which equations, which equations are correct. This is the question, and we'll have a set of equations, and we have to identify that for polar coordinates which equations are correct. So let me write down the equations. So equation A is that cos theta is and sine phi is. So you will note that these equations are relating the Cartesian coordinates with the polar coordinates. Okay, these equations are relating the Cartesian coordinates with the polar coordinates. So this is option A. Let me write option B. And option C. Finally, option D. Okay, so basically different values of cos or sine theta and different values of cos or sine phi or tan phi, and we want to write all these things in terms of x, y, and z. So if we move back to our diagram here, so one thing that we note straight away, that this r is the distance of the point P from the origin, right? So r is the, so if origin I am denoting by O, so r is the distance OP, right? And we know how to write this distance. We can simply write this as square root of x squared plus y squared plus z squared. Okay, so now we have already written r in terms of x, y, and z. This is simply the distance. Okay, so now if you look at this length, so let me write this point as q. Okay, if you look at the length OQ, we know that this will be z, right, in the Cartesian coordinates. So this point is at a height z, right? So this point is at a height z. So this length will be OQ will be z. Now this is z and this is r, and this makes a 90-degree angle. Okay, this makes a 90-degree angle. So from this triangle OPQ, from OPQ triangle, what we can write? We can write cos theta, right? We can write cos theta, and cos theta is base upon hypotenuse, right? So cos theta is base upon hypotenuse, and here base is z and hypotenuse is r. Okay, so we can write cos theta to be z upon under root x squared plus y squared plus z squared. So we have found cos theta. Okay, we have the equation for cos theta. Now we need one equation for phi. We need one equation for phi. Now note that this OP prime, okay, so this OP prime is equals to QP. right? This length OP prime and this length QP, they will be same, right? This is just a rectangle. So what will be this QP? This will be simply R times sine theta, right? So we write cos theta as Z by R, and then we can write sine theta as QP by R. So then we can write QP as R sine theta. And then because these two are equal, we can write OP prime, which is this length. This will be nothing but R sine theta, right? This is R sine theta. And then we want to write phi, okay? So let us draw this rectangle here. In the xy plane, I am drawing one rectangle. This one. Okay, now this angle will be 90 degrees. Okay, this angle is 90 degrees in the xy plane. So let's say this point is PQ. Let's say this point is, I don't know, M. Okay, let's say this point is M. So from the triangle MOP prime, from the triangle MOP prime, what we will get? We will get that our OM, which is nothing but x, this is just x, right? This distance is x. We can write this as OP prime cos phi. We can write it as OP prime cos phi. Okay, so finally we can write cos phi, we can write as x upon OP prime, which is nothing but R sine theta. Okay, and we already know cos theta, so we essentially also know theta. Now let's have a look at our options. Okay, so yeah, so we have already calculated the value of cos theta, and you can see that it matches with option B. Okay, rest all are wrong. Yeah, so option B is correct. Let us check if this tan phi is equals to y by x. Okay, yeah, it's fairly straightforward to check. So this is phi, and in this triangle MP prime, this distance is y, right? This distance is y. So if you take tangent of phi here, we'll get tan phi. This will be y over x. So option B is correct. Yeah. So in general, what we can write, if we want to go from one coordinate system to the next one, so in general, this is how you go. So if you are given r theta and phi, you can write x as r sine theta cos phi, y as r sine theta sine phi, and z as r cos theta. So this is in general the transformation rules or the transformation equations. Equations from the polar coordinate systems r theta phi to your Cartesian coordinate system x, y, and z. Okay, so this is how we connect the two coordinate systems. Okay, now let's solve few quantum mechanics problems related to operators. Okay, So we have this operator, and it operates on a given eigenfunction. So we have an eigenfunction. It is given to us that psi of x is, this is an exponential function, but it has iota in it, where this iota is square root of -1. So this is our imaginary number, right? And a is a constant. So what will be the eigenvalue? So this is the question. And these are our options: 0, 1, a, or a squared. Okay. Now so if you have any operator, let's say d. So if d is an operator, which operates on a wave function f of x, okay, and gives the result k times f of x, where k is some constant, then k is called eigenvalue. Okay, this is the definition of eigenvalue. So writing it mathematically, so operator d operating on f of x will give you k times f of x, where this is operator and this is eigenvalue. This is the eigenvalue. So here operator is given to be minus d over dx squared, and we want to find out the value of eigenvalue, and fx is given to be a e I x. Okay. Yeah. So yeah, let's solve this. Then we have to just operate the operator on the eigenfunction. Okay. So let's do it. So we have to then basically compute the value of minus d2 over dx squared, and the function is a e iota x. So this is what we want to compute. Okay, let me rewrite it like this. So this is equals to, so we take one derivative and then we take another derivative of the same function. Okay, so upon taking the first derivative, what we will get? So a is a constant, it will come out. And derivative of an exponential function is the exponential function itself, and we'll just get one iota outside. Otherwise, it will remain the same. Okay. Now we differentiate it again. And we have a minus sign here. A is here, I is here. So again, we will get one more I, and the function remains like this. Now I squared is minus 1, right? So I squared is minus 1. So this becomes a times e to the power iota x, which is our function with which we started, right? So this is just psi. Okay. So now we note that when we operated d psi, we got psi again. Okay. So what is the eigenvalue? So eigenvalue is simply, so if we compare this equation with this equation here, we note that k is 1. Okay. So this is our eigenvalue for this problem. So k is 1, which means option number B is the correct option. Yeah, so a fairly simple problem. If you have anything to ask, you can ask. Otherwise, we'll move on to the next one. Okay. Question 9. Find the energy of a particle of mass m in a one-dimensional potential well in a 1D potential well, and length is given to be L with following boundary conditions. So we are given some boundary conditions for a one-dimensional potential well, and we are asked to find the energy of a particle in the well. Okay, and the boundary conditions are that our potential energy is 0 for x greater than 0 less than L, and it is infinite for x less than 0 and x greater than L. Okay, so this is the problem. Okay, now yeah, this is the standard problem, standard 1D potential well, and you might also know the answer just right off your head, but because this was not solved explicitly in the class, I thought maybe I'll put out a solution in case anyone doesn't know. Okay, so if we draw the diagram, it is very similar to problem 1 which we solved today. Okay, so this is your x-axis, and let's say this is your x is equals to 0. So here your potential energy diverges, it becomes infinity, and again at x is equals to L, so this is 0, this is L, so it diverges. Okay, so this is like a hard wall problem. So you cannot have a particle in this region, and you also cannot have a particle in this region. So this is therefore called a one-dimensional potential well, or an infinite well, because the potential is infinity at the boundary. So probability of finding the particle in this region is 0, and also in this region the probability is 0. So this is the problem which we are now. What we are interested in, we are asked to find the energy of particle. Okay. So firstly, one thing to note that is that the probability being 0 means that our wave function psi of x, that is 0 here, and similarly we can write psi of x is 0 here. And now note that there are boundary conditions, and so there are some rules that psi of x has to be continuous everywhere. Which means that when we put x as 0, it will be 0, and when we put x as L, again it will be 0. So this comes from boundary conditions, right? And the fact that psi x has to be continuous. So these two things, they tell us that psi is 0 at the boundaries. Okay. Second thing is that psi prime of x, which is the first derivative, that also has to be continuous. Psi prime of x also has to be continuous. So we'll see if we need this one or not later. Okay. So then first we can write when particle is inside the box, we can write the Schrodinger equation. Okay. So we have different regions. So for the motion of the particle in one dimension inside the box, so when particle is inside the box, then it is given that the potential energy is 0. It is given here, right? It is given. So the Schrodinger equation, which is minus h cut squared over 2m t2 psi over dx squared. So this is the kinetic energy term, and potential energy is simply 0. So this is equals to E psi. This is the Schrodinger's equation. Schrodinger's equation. Okay. Now here E is the energy of the particle. So because this is 0, we can rewrite this. We can rewrite this like this. So then this is just equals to E psi. Okay. Now again we can rearrange. Yeah, we can rearrange it like this. And finally, just one last rearrangement. We can write it like this. Okay. And let's say I call this thing, let's say we call this thing as k squared. Okay. Just a change in notation, nothing else. Then our equation becomes d2 psi of x over dx squared plus k squared psi of x is 0. Now this is a second order ordinary differential equation. Okay. So this is a second order ordinary differential equation. Okay. And the general solution of this psi of x, it can be written as a sine kx plus b cos kx. okay, where a and b are some constants. So a is a constant, b is a constant. Now what we do is use boundary conditions. Okay, use boundary conditions. Let us use boundary conditions. So at x equals to 0, psi of x is 0, which implies a sine k 0 plus b cos k 0 is 0. Now note that cos of 0 is 1, okay, and sine of 0 is 0. So this equation simply implies that b is 0, okay, because this is 0 and this is 1. So for this equation to be true, b has to be 0. Now at x equals to L, again psi of x is 0, which implies that a sine kl, this has to be 0. Now this would mean either a is 0 or sine kl is 0. Now if we take a is 0, so this is a trivial solution. This is a trivial solution and it will not give us many meaningful things. So if both a and b are 0, then our wave function psi is 0 everywhere and we do not get any meaning from that. So let's say we consider the second case when sine kl is 0. And when is a sine function 0? Sine function is 0 when your theta, this is equals to n pi. Okay, when theta is n pi. So here theta is kl. Okay, so yeah. So from here we get k as n pi over l. This is, let's say, equation 2. Okay, and we already had equation 1 here, that k squared is 2me over h cut squared. Okay, let's rewrite both of them. So we have k squared is 2me over h cut squared, and from this equation we have k squared will be n squared pi squared over l squared. So we can then equate both the equations. And what we will get is 2me over h cut squared is nothing but n squared pi squared over l squared, or the energy E will be n squared pi squared h cut squared over 2 m l squared. Okay, or if we write h cut as h over 2 pi, so this pi square term will cancel out and will only remain with h, and this is the final energy which we will get. Okay. Yeah, so this is the energy which we are getting. And in the earlier problems, problem 1 and 2, we just directly used the value of energy, but here we can solve this explicitly and we will get the required energy. Here I would just mention that n goes from 1, 2, 3 and so on. Okay, and we can also write out our wave function psi. So this was just a sine kx, and k we have got to be n pi x over l. So this is our wave function. Now if we normalize this such that, so this is the normalization condition. Okay, so I think this would give a to be under root 2 over L. Okay, then finally we can write sine psi as under root 2 by L sine n pi x by L. Okay, again n is 1 2 3 so on. Okay, so we have successfully calculated energy and wave function for a one-dimensional potential wave. Okay, any doubts? No, so let's solve the next one. So the next one says that for a 1D box, normalized wave function is given as, which we just calculated. Okay, this is the wave function or the normalized wave function. Okay, now the question is find the probability find the probability of finding the particle in the box in a region from L by 4 to L by 2 for the first excited state. Okay, and here we are given some options: 25, 30, 40, 50. Okay, let us draw the potential box again. Okay, let's say this is our potential box and this potential here is infinite, and again the potential here is infinite, and in between the potential is 0. Okay, now what will be L by 2? This will be L by 2 and this will be L by 4. So what we are asked is that in this region so this is the region, right? Yeah, so this is the region, and in this region we want to find the probability of finding the particle in its first excited state. Okay, so remember we are talking about first excited state. Okay, now how do you define probability? Okay, so let's get started. The probability of finding the particle So let this be P, and this will be integral from L by 4 to L by 2 mod of psi n dx. This is how we define probability. Okay, so this is just definition in quantum mechanics. This is how probability is defined. So from your starting point, which here is L by 4, to your end point, which here is L by 2, we just take the square of the mod psi, which is the eigenfunction, and then we integrate. So this integral upon solving will give us the probability. Okay. Now what is psi? So psi n is under root 2 by l sine n pi x by l. And what is first excited state mean? Okay, n is equals to 1 means ground state, and n is equals to 2 will mean first excited state. And because the question asks about first excited state, so we have n is equals to 2 here. This implies that our psi 2 will be under root 2 by l sine of 2 pi x over l. So this is the wave function. Okay, now we want to get to the probability. Let me write here. Just draw a line. Okay, so we can write P as integral L by 4 L by 2 and what will psi square give us? So psi square will give us 2 by L sine squared 2 pi x by L dx. Okay, so this is the integral. Good. Now we can take this 2 by L outside and we can integrate from L by 4 to L by 2. And now we know that sine squared theta, this we can write in terms of 1 minus cos 2 theta divided by 2. Okay, so this is a trigonometric identity. This is a trigonometric identity which we will be using. So this will just then become half of 1 minus cosine 2 theta. So then this will become 4 pi x by l and dx. Okay. So now we get two integrals. This 2 will cancel out. So we can write P as just 1 by L and then integral from L by 4 to L by 2 or just simply 1 times dx minus integral of L by 4 L by 2 cos 4 pi x by L times dx. Okay. So this integral will simply give us L by 2 minus L by 4, just putting in the limits, right? And integral of cos is sine. So integral of cos is sine, but here we also have this 4 pi by L. So this will become L over 4 pi and sine of 4 pi x over L, and we have to put in the limits L by 4 L by 2. Okay, so here we are. So 1 over L L by 2 minus L by 4 will become L by 4, and this will become L upon 4 pi. And now let's put in the values. So so if you put x as L by 2, it will become sine of 4 pi by 2. So this will become sine of 2 pi. And if you put L by 4, this will become sine of pi. Okay. And now what is 2 pi? 360, and sine of 2 pi. So this term is simply 0. And again sine of 180, this term is also 0. So we can forget about all these terms. And finally we'll just get 1 over L into L by 4. And this is simply 1 by 4. So writing in terms of percentage, we get P as 1 by 4, or this is nothing but 25 over 100 or 25%. Okay. So this is the probability of finding the particle between L by 4 and L by 2 in the first excited state. Okay, correct answer is option A. So there is a 25% chance that we find the particle. If we do a certain measurement to find the particle, there is a 25% chance that we will find a particle between L by 4 and L by 2. Okay, any doubts in this one? No? Okay, then let's do one last problem. So one last problem for the day, and then we'll call it off. So let me write down the problem. So this will be problem 11. Yeah. So problem 11th. Yeah. So what is the problem? This problem I have taken from Zetli, which is a very nice book on quantum mechanics. So the problem is that you have a particle of mass m. We have particle of mass m. Okay. And this particle is inside a 1D well, just like the problems we were solving before, and the length of the well is A. This is the length of the well. Okay. So a particle of mass m inside a 1D well of length A is initially in the state so psi x at time t0. Okay, so this is initially in the state under root 3 over 5a sine 3 pi x by a plus 1 over under root 5a sine 5 pi x by a. Okay, and the problem is find psi xt at any later time t. Okay, so we are given the wave function at time is equals to 0, and we want to find the wave function at any general time t. Okay, now one thing, we can actually rewrite this thing. Okay, so we know that for a 1D potential well. Okay, so for a 1D well, we know that let me denote the wave function by phi, because problem is already using psi. So we know that phi n of x, the normalized wave function, is root 2 by a sine n pi x by a. Correct? So if now we look at this wave function which is given to us, we can actually write psi x of 0 in terms of this phi n, right? So if we write this thing, as, so what we have to do, so we have to write under root, sorry, this will be under root 3 by 10. Okay, and then here you can see n is 3, so this will be phi 3. Okay, and here it will be 1 over root 10, 1 over root 10, and here you can see n is 5, so it will be phi 5x. Okay, so this is your second excited state, and this is your fourth excited state. So here you have n is 3, and here you have n is 5, and again we can check that the entire wave function psi is also normalized initially, so we don't have to worry about normalization, and we only have to worry about the energy term. Okay, now for any wave function, okay, I'm running out of symbols. Let's say for any wave function f, okay, if we are given f at x equal to 0, then f at some time t, this will be f at x equal to 0, and then we multiply it by e to the power minus iota e t by h cut. Okay, this is how we from the initial condition, from t is equals to 0, we can write the wave function at any given time t. Okay, if we know the wave function at time t is equals to 0, we can write for any time t like this. So we take the initial wave function and then simply multiply it by this term. Now here, one thing which we have to be careful about is that energy for phi 3 will be different and energy for phi 5 will be different. Okay, so our psi x of t, sorry, so our psi x of t, this will look like psi x 0. So I will write psi x 0, this thing, and then multiply this, and then I will multiply this with e to the power minus iota e3 t over h cut, and similarly this will be 1 over root 10 phi 5 of x multiplied by e to the power minus iota e5t by h cut. Okay, so what will be e3? So e3, we know that it will be, so n is 3, so 3 squared is 9, h squared over 8m a squared. Similarly, e5 will be 25 h squared over 8m a squared. So finally, we can write psi x of t to be like this. So this will be phi 3x e to the minus iota, and 3 is just 9 h square h, sorry, it will be 9 h squared t over 8m a squared h cut, and this term will be 1 over root 10 5 of x e to the power minus iota 25 h squared t upon 8m a squared h cut. So this is the wave function at any given time. Okay. Now let's do its b part. So b part asks us to calculate the probability density rho. Calculate the probability density rho xt and current density j xt. Okay. So this is the second part of this problem. Okay. Now how do you define the probability density? So probability density rho, this is defined as psi star psi. This is the probability density. Okay, so here we can write psi xt. We already know this psi, we have already calculated psi here. So what we will get is, we will get 3 over 10, right? We will get 3 over 10 phi 3 squared, okay, plus under root 3 by 10 phi 3 phi 5, this is x, and then here we will have, inside we will have this term e to the power iota e3 minus e5 t by h cut, and plus e to the power minus iota e3 minus e5 t by h cut, bracket closed, and finally we will have 1 over 10 5 squared times x. So this will be the probability density. Now if you see, this is like e to the power I theta plus e to the power minus I theta. So this just becomes cosine theta, right? 2 times cosine theta. So this will become 3 over, okay, maybe I should write down. This will become 3 over 10 phi 3 squared of x plus, because this is 2 times, so 2 and 10 will cancel, will give you 5, plus root 3 by 5 phi 3 phi 5, and this becomes cos 16, okay, this becomes cos e3 minus e5 times t by h cut, cos of e3 minus e5 times t by h cut. So it becomes this. Okay, and finally we have 5 squared over 10. Now e3 minus e5, let's write it down. So e3 minus e5, this is nothing but, this will be 9h squared over 8m a squared, right, minus 25 a squared over 8m a squared, okay. So then this is simply minus 16h squared over 8m a squared. And now we'll plug it here. We'll plug it here, and what we'll find is that our rho therefore can be written as 3 over 10 phi 3 squared plus under root 3 over 5 phi 3 phi 5 cos of cos of, so this just gives you 2. Okay, yeah, so cos of 2 h squared t over, so h cut is h over 2 pi, so this into 2 pi goes here, and m a squared comes here, so cos of this and plus 5 squared over 10. Okay, so this thing. And finally we can also write down the wave functions. So this will become 3 upon 5a, because this is under root 2 over a, sine squared 3 pi x over a plus 2 root 3 upon 5a sine of 3 pi x over a sine of 5 pi x over a. So this is 5 3 and 5 5 multiplied, but there is also one cosine term multiplied with this, which is just cos of 4 pi h squared t, no, so this will be just h now, 4 pi h t multiplied by m a squared, and lastly 1 over 5a sine squared 5 pi x pi. So this is our rho xt, which is the probability density at any given x and any given t. Okay. Okay, so I think it's already 5 p.m. So okay, so what we can do is we can continue with this problem in the next class. Okay, so we have calculated rho, and in the next class we will calculate the current density J, and then there is a follow-up question which asks us to verify the probability conservation. So in the last part we will verify that the probability is conserved, which is the continuity equation. Okay, so yeah, I guess that's it for today. Thank you for joining, and I will see you next Saturday, 3 p.m.